Hello, chemistry students. This is Professor Sean McMahon, and today I'll be lecturing in this video for Chapter 4, Atoms and Elements. I'll talk a little bit about atomic structure, the periodic table, elemental symbols, and how to identify the elements based on their atomic number and the elemental symbol. But before I go and start Chapter 4, I kind of want to do a warm-up exercise where we left off with Chapter 3, which was matter and energy, and doing some of the heat calculations. The reason why I'd like to do that is students, there's different types of calculations when using energy calculations and when we were using specific heat. So as a review, let's try this heat calculation problem. Calculate the heat necessary. So right away, I know I'm looking for heat. And if you remember, from the Q equals mCAT that we talked about, heat is Q. So I want to calculate the heat. I'm looking for Q. So I probably need mCAT. So calculate the heat necessary to warm a 3.10 gram sample. So I already know the mass of the sample of copper. So now I know that it's copper from a negative 5 degrees Celsius to 37 if the specific heat capacity of copper is 0.385 joules per gram degree Celsius. So I'll reread that without interrupting, kind of calculate the heat necessary to warm this mass of copper from this temperature to this temperature. So with mCAT, the delta T, there's an initial temperature and there's a final temperature. Okay, so I'm raising this mass of copper from that temperature to that temperature, and I want to know how much heat is required. But I need to know in the mCAT the specific heat, which is the C, and they give this. Now, they don't have to always give this to you in the problem. Sometimes you might have to refer to a table or in your book to find the specific heat of copper. And again, it could be in calories per gram degree Celsius, and I'm sorry, the degree Celsius came over here, it'd be right here. Or it could be in joules per gram degree Celsius. So because it doesn't tell us what unit for heat, we'll leave the unit in terms of joules. So Q equals mCAT. I'm solving for heat. I plug everything in. Now, where did I get for the mass? I know I got the 3.10 grams. For the specific heat, I got the 0.385 joules per gram degree Celsius because I either looked that up or it was provided. How did I get this? Remember, delta T is always final. Anytime you see a delta, whether it's delta V, change in volume, it'd be final minus initial. This is delta T, so it's final minus initial. And if I go 37 minus a negative 50 or negative 5, I use my rules for addition of a negative and it becomes positive. And 37 plus 5 is where I get the 42 degrees Celsius. Then I also see in the formula the grams cancel and my degrees Celsius because I want to make sure the units cancel, just like with the conversion factor. I get the answer for 50.1 joules. The reason why there's 3 sig figs is a lot of times students get confused because they see the 5 and they think, hey, that's only 2 sig figs. But remember with the delta T, because it's a subtraction, we follow a different rule. We're going 37.0, which is to the tenths, minus 5.0, which is to the tenths. So I'm actually adding these because it's minus a negative. Following the rules of addition subtraction, I go to the least precision, the least precise measurement. Well, both of these go to the tenths, and that's why the 42.0, I add that trailing 0 to show that this measurement, based on the precision of the device, goes to the tenths place. So this is 3 sig figs here, just like this, and that's why my final answer has 3 significant figures. Let's do another one, because you're not always going to be asked to solve for heat. I think in the last lecture, we had you solve for specific heat. Let's do one where we're trying to figure out the final temperature. Okay, so I have a 328 gram sample of water and it absorbs 5.78 kilojoules of heat. If the water sample has an initial temperature of 35.3 degrees Celsius, what will be its final temperature? Now, liquid water is the only specific heat I expect anybody to know because it's kind of the reference point for all specific heats. And if you remember from last lecture, it was relatively high compared to metals and other substances. So the 4.184 joules per gram degree Celsius for water, and again, I'm sorry, this keeps dropping, is the one you should know. That's like the only one. It's also, remember, if you remember, 1 calorie per gram degree Celsius, because 1 calorie is equivalent to 4.184. But I already know that there's a change in temperature. I'm giving you the specific heat of water, right? And I'm giving you a unit of kilojoules, which is for energy, which is heat. So I'm going to use Q equals mCAT, all right? And remember, I'm looking for a final temperature. They give me the initial temperature of the water at 35.3 degrees Celsius. But what I'm going to do is I'm just going to solve for delta T first. And then once I have the delta T, I'll plug in my initial temperature and then I'll solve for final temperature. I personally feel that's easier than doing excessive distribution. But you don't have to do it my way. You can do it any way you want. Okay, so delta T, that's what I'm solving for so that I can get the final. If I rearrange this algebraically, I'm dividing both sides by the mass and the specific heat. And that's how I get that equation. Now, I need to be careful because the heat that was given to me was in kilojoules, not joules as in the unit for the specific heat of water. So what I need to do, because I need those units to cancel and to agree with each other, I need to use a metric system and convert the kilojoules to joules. Now, I cheated. I use exponents, but really 10 to the 3 is 1,000 joules per 1 kilojoule, right? Because there's 3 zeros and scientific notation is base 10. So because there's 3 zeros and it's bigger than 1, the exponent is a positive 3. Now, why did I do that? Well, now this is really easy because the kilojoules cancel. And when I plug it in to the Q divided by MC, I just have it already in scientific notation as 5.78 times 10 to the 3 joules. That's why I did it that way. Again, you don't have to, but it just makes it easier. Then I plug in the mass that was given, the 328 grams, and then I plug in the specific heat for water, which again is the one that you should know. The rest of them you can look up, they'll be provided, no one expects you to know. But water, you're kind of expected to know, it's the reference point. And when I look, here's the 4.184 joules per gram degree Celsius. So I get the grams to cancel, the joules cancel, and really if I look in terms of unit, I have 1 over 1 degree Celsius. So because this is in the denominator of this quotient, that's in the denominator of this, it ends up being like, 1 divided by 1 over C, which really, I just flip this and it's like 1 times your degree Celsius. So that's why I'm left for delta T. Oops, sorry, 1 over. For delta T, I'm left with the unit of degrees Celsius, and it's 4.2, okay? Now, a lot of people are getting confused. Well, why is there only 2 sig figs? I could have put, in actuality, 3 sig figs here, and then that would, go to the hundredths. The reason why I'm doing it to the tenths is because what's going to actually happen is when I plug this delta T in here, and I'm going to have, minus the 35.3. Remember, this is to the tenths. So my final answer is going to be to the tenths regardless. And now I'm not using multiplication division rules. I'm using addition and subtraction. So I go to the least precise, which for this temperature measurement will be to the tenths. To get rid of the 35.3 on this side and isolate the final temperature, I add it to both sides. And I get the final temperature for a 328 gram sample of water that absorbs 5.78 kilojoules starting at a temperature of 35.3 degrees Celsius. It rises to a temperature of 39.5. So that's a lot of heat. And there's only a little bit of a change in temperature. And that's because water has such a high specific heat. So that's kind of the warm up. That's where we left off in chapter 3 with those energy calculations, focusing on the heat energy. And they're really common calculations. You'll see those in the chapter 3 homework that I assigned. So I just wanted to give you a little more practice. The good news is now we get to new stuff. We get to chapter 4, atoms and elements. And in this particular lecture, there's not really a lot of calculations. There's some simple arithmetic, but there's really not much. We're just going to talk about the periodic table, essentially, because remember from our last lecture, matter, element is the plural and the singular is atom, okay? So where do we get elemental names, right? Where do we get the elements' names? Well, a lot of these were named long before the English language was so common, right? So, but some of them are mythological, some are from planets, they're from colors, minerals, scientists, places. And I always like to show, well, like uranium, right? That's from the planet Uranus. Titanium, the Titans. Chlorine, chloris, which is greenish yellow color. I'm not going to even try the iodine, but violet. And you can see magnesium, magnesia, mineral, californium for California, and curium after Madame Marie Curie. So this is different ways that we came up with these names. So we don't always write out the full name. In fact, when you look at the periodic table of elements, a lot of them just show the elemental symbol. So this is a shortcut. You can think of it as shorthand to write things out by just using 1 or 2 letters. So it's a lot quicker to write 1 or 2 letters than the full name. All right. So typically the first letter is capital. If there is a second letter, it's going to be lowercase. All right. So here's some examples. Carbon. We see that carbon, right? It's capital C. Now for a 2-letter symbol, we have cobalt. And the reason why it's not just capital C is then we would get confused with carbon. So what do? We go to the second letter of O and we put it in a lowercase. So nitrogen, capital N. Calcium, same situation that we had with cobalt. Capital C alone was already taken by carbon. So what do? We go to the second letter, we lowercase it, and it's Ca. And I know a lot of you already know these symbols. That's why I'm using these specifically. Again, fluorine F, oxygen O. However, for aluminum, we do Al, magnesium, Mg, not to be confused with manganese, which is Mn. Okay. So the other thing that students notice when they look at the periodic table, they might see, you know, copper is Cu. Well, again, that's because when it was originally named, it was cuprum, right? We've heard of the Copper Age, right? That was a long time ago. So the name for copper was cuprum. So now we use Cu because that name has carried throughout history. Gold, aurum, Au. Okay. Iron, right? Ferrum, silver, argentum. Now, Argentina was named after Argentum because it was believed that it was just a mountain of silver, right? So these are some other symbols that you might see. But if you notice, they're all 2 letters, right? They have the first letter capitalized and the second lowercase, but the name is derived from the Latin name because that was the more, you know, common language at the time that these were first kind of identified and named. And we just carried that through history. Why change it? If it works, don't change it. So we have to kind of be able to match symbols with the names. So typically when I do these exercises, it's not a bad idea if you're watching the video, right, to pull out a periodic table. Now, if you see a periodic table, you'll see that N stands for nitrogen. P, phosphorus, and Ag we just went over with silver, okay? So if you don't have a periodic table, go ahead and pause the video, grab it. You can use your book. But I'm gonna kind of talk about now, we have the periodic table. We're aware that there's names, but how is it organized and why is it organized the way it is? So originally Mendeleev was the first to organize it. And what he did was he arranged all the elements according to repeating physical properties and patterns. And it was called the periodic law. So at first, if you just take all the elements that that was known at the time and line them all up, you'll see that some had some common patterns, like lithium kind of matched sodium and potassium, right? And beryllium matched magnesium and calcium. And helium was matching neon and argon. So instead of doing one continuous row, what we ended up doing is whatever's similar, we put it in a column, in a vertical column. So we organize, and this is a very simple periodic table, just to kind of give you an idea. This is what's considered the representative elements, but whatever has a similar property, now we put them in columns instead of just one long row, and we get something like this. So he did leave blank spaces where he thought future elements would exist and match that column in its physical and chemical properties. And he did it quite accurately. In fact, he was able to use the periodic law. Now, if you remember the scientific method, okay, we talked about, oh, heck. Heck were the conclusions that you could draw after experimentation, collection of data, making your observations, analyzing your data and your results so that you can draw conclusions. And I said there were two types of conclusions. There were laws, which explain pretty much what would happen, and theories that explained why it happened. So Mendeleev, he wasn't really focusing on why things were happening. He was just trying to predict patterns, kind of like if you've taken math, arithmetic and geometric sequences. So he was recognizing patterns, and this allowed him to predict an unknown element that would go below silicon, because there was a gap in that vertical column, and the properties. So EKA silicon. And his predictions were, okay, it's going to be gray. Its density is going to be 5.5. It's going to have a high melting point. It'll combine with oxygen, 2 oxygens to 1. The formula, the boiling point. And surprisingly, right, in 1886, it was discovered germanium, and it was discovered that it actually, has very similar properties based on its prediction, because that's what a law does. It tells you what's going to happen. And it was a very valid prediction. So now we use a periodic table because it helps us understand what to expect from the elements, how to identify them. And when we get into atomic theory, which we do later in this chapter, we'll understand not just what's happening, we'll understand why. But this particular lecture is focusing on the periodic law and why. So the way the periodic table is organized right now, it's based on what's called the increasing atomic number. What I want you to think of is atomic number is really just the number of protons in an atom of that element. Okay, remember, atom is singular, right? If I just had one atom, that would be an atom. If I had multiple atoms of the same type of atom, that would be called an element, the plural. So when I look at a periodic table, right, I can see that it's organized based by increasing numbers. So, hydrogen is the first element in the periodic table. Well, why is that? Its atomic number is 1. Well, what does that mean? It has 1 proton. Then helium is the second. Why? It has 2 protons. Lithium is the third. And the reason why we're restacking is we're matching the properties based on columns. Okay, beryllium is the fourth. Why? Atomic number 4, it has 4 protons. So by understanding, right, that we're organizing it by atomic number, that helps us to identify elements and where they're located, because I could give you an atomic number and you can go across, let me go back, and you can go across a periodic table and find it. So if I said, for example, which element has atomic number 16? You would go across and be like, oh, that's sulfur. Sulfur has an atomic number of 16, which means it has 16 protons. Another way to locate elements is by using the columns, okay? So a column, right? You can think of it as going up and down. They're also referred to as groups or families, okay? We can also use rows, which are actually called periods. And I'll even refer to these in this chapter when we talk about electron arrangement as energy levels. Okay, so you can call them periods, series, energy levels. But what it does is that helps me. If I told you, all right, on period 4, group 2, write the elemental symbol. You could easily go, okay, well, here's period 4. How do I know that? Here's 1, 2, 3. This is the 4th row. All right. That's my period. And in group 2, well, what do I mean by group? Column 2. So here's column 1, here's column 2. Oh, well, the element that's in period 4, column 2 is calcium. So then I would write Ca. And maybe someone might even say, well, what's the atomic number or number of protons? And you'd say, oh, well, I could easily identify it. There's 20. That element has 20 protons in the nucleus. That's what makes it calcium. So when you look at the periodic table, we can use the group numbers to find the columns, right? And we read left to right. So the first one is group 1, right? And then we notice, okay, there is kind of this little valley right here. There's a valley of 10 spots, okay? Those are your transition elements, okay, or transition metals. So there's an older system and there's a newer system. The newer system just labels, you know, the number, so 1, 2, and then goes across 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So when I get here, it's 13 all the way across to 18. The old system kind of, it's not that it's ignoring, it focuses on what's referred to as the representative elements, the bigger blocks that don't have the valley, the more commonly discussed elements. It looks at the representative elements and it gives it a letter A to distinguish it. So now we see it's 1A, 2A, we skip the transition metals and we go 3A, 4A, 5A, 6A, 7A, 8A. And we notice the difference is just the 10, right? Because 13 minus 10 would be 3. So the old system ignores that valley of 10. The letter B, oh, I wrote all over here, I'm so sorry. The letter B is to denote the transition elements, the transition metals. So those are the ones in the valley. Now, we talked about how Mendeleev looked at all the elements and kind of stacked them in these groups and families based on similarities and properties. And now what we notice, and our focus again, is going to be the representative elements, the two big blocks rather than the block in the valley. So this is kind of my valley, the transition elements. When we look, we can give these groups names. So like group 1A is considered an alkali, considered an alkali metal, right? Group 2A is alkaline earth metal. So if I put these metals in water, I make an alkaline solution. So a lot of people are becoming aware of alkaline water and things like that, that means it's slightly basic. So if I put these metals in water, they're so reactive, they react with water, and they end up producing not just a base, but release gas and a lot of heat as well, okay? If I go on the far side, this group, okay, is really, all the elements want to be group 8A. Why? They're noble gases. Everybody wants to be noble, right? Well, the reason why they were given that name is these tend to be the most stable, okay? We'll find out in future lectures. The reason why they're stable is they have a period that has all the electrons filled in that period. I call it energy levels. You may think of it, if you're familiar with the Bohr model, as orbits of electrons around a nucleus. When we talk a little bit about quantum in this class, we don't do too much quantum, but we'll refer to it as orbitals rather than orbits because they're not necessarily fixed. They're a region of space where the electrons occupy. But essentially, the noble gases have their, period, their energy level, their orbit or orbital filled. That's what makes them so stable. All these other elements are trying to be noble gases and fill that energy level with electrons. So they're willing to lose or take electrons or share electrons to fill that outer energy level, okay? Right next to the noble gases, we have halogens. Now, halogens are very reactive too, okay? For a different reason, but they are extremely reactive. And then for this block, we just would say, this is group 3A, okay? So let's try to figure out the group for these. And if there's a name for the group, let's give a name. So what we're going to need is a periodic table. Now with this periodic table, it might be a little hard for you to see, but I just put it up there to remind you, it's nice to have one. Notice I didn't color code it, right? I don't want to cheat and make it easy for you. I want you to be comfortable with it, right? So it's not color coded. The names of the families aren't there, but you can still quickly, you could identify, where's bromine? So if I look, bromine's right there. Now that was right next. This actually shows you that this is noble gases. And the one right next to group 8A is 7A. Now, how could you figure that out? Well, 1, 2, 3, 4, 5, 6, 7, 8. Remember, I'm skipping the middle, but really I should be saying A for all of these. So group 7A are the halogens. Now, where's nitrogen? Remember, that just had a common name, so nitrogen's group 5A. Cesium, I go here, it's in group 1A, and that first group had a name of alkali metals, and then magnesium, it's right there, group 2A, alkaline earth metals. So that's a way that you can quickly identify, I could also say, group 7A in period 4, what's the element? So I would go to period 4, go all the way to 7A right here, and I'd be like, oh, that's bromine. And then I would write the elemental symbol Br. Okay. So when we look at the periodic table, we notice that there's a little like highlighted staircase right here. And this periodic table is nice. It's kind of color coded for you. But about 3/4 of the elements are metals, okay? So what does that mean? Well, typically metals are solid at room temperature. They're shiny and lustrous. That's why they were desired in the past, right? Copper, gold, silver, right? They conduct heat and electricity, and we know that with copper wiring, right? Pans are made of metal, right? And they're malleable and ductile. Malleable means I could bend them. So I could heat up, iron and hammer it into a sword or a weapon. Ductile means I could draw it out into long threads and strings like copper wiring. Now the remaining elements are pretty much classified as non, right? So over on this side of the staircase are the metals. And then on this side are your nonmetals. Okay, so the staircase is very powerful. It lets me know, okay, if I'm on the left side of the staircase, metals. If I'm on the right, nonmetals. And again, there's fewer nonmetals. And most of the nonmetals are actually gases. If they are solids, they're not reflective. And you can see that in the case of sulfur right here, right? Most of the time, they're non-reflective. They don't conduct heat or electricity, and they're brittle if they're a solid. So everything that, I can't hammer them into shape like phosphorus or sulfur, right? So they're everything that a metal isn't. They're like the opposite. So that makes it kind of easy. If I know what metals are, non-metals are just the opposite, right? They're not shiny, they're not lustrous or shiny. They're dull in color. They don't conduct heat and electricity. They're not malleable, they're brittle, okay? But there are a few elements that are, they're in the middle of the spectrum. They're not on either complete side, right? Because there's a full spectrum of characteristics. And those are your metalloids, okay? So they tend to have properties of both metals and non-metals. So here's an example of metal, non-metal, and a metalloid, okay? And really, the silicon is your metalloid. So, I could have probably switched this and moved it here to make the PowerPoint a little better, but that's okay. But if we look at silver, which is a metal, what do we know? Well, it's shiny, right? I can shape it. It conducts heat and electricity. Well, what about sulfur? Dull, it's brittle, doesn't conduct heat or electricity. Well, what about silicon? Silicon Valley, metalloid. It's a solid. It's a little shiny, right? But it's brittle. I can't really hammer it into shape very well. And it doesn't conduct heat as well. It's a semiconductor. And it's it's a semiconductor for electricity. Okay. So can you identify each of the following elements as either now? So before, I was saying, look at a periodic table. We can, instead of write out the full name, write the elemental symbol, just 1 or 2 letters. Then I can organize it by groups or families, right? Columns and periods. Or the atomic number, right? The number of protons. Now I'm saying, I just want you to tell me, is it a metal or a non-metal? And what I'm going to use is that staircase. Right? So this isn't color-coded at all, because I want you to get comfortable without that luxury, right? But I know on the left side are my metals, and then on the right side are my non-metals, and I'm hugging along that staircase for metalloids. So sodium, where's sodium? Right? So that would be a metal. What about chlorine? That'd be a non-metal. Silicon, we know, because I just had that on the previous slide, right? That would be a metalloid. Iron is in this little valley right here, which was called the transition elements or transition metals. All right, so that's still a metal because it's on the left side. And then carbon, which is on the right, non-metal. But to help you with your valley, let me erase the circles. Or to help you with the metalloids, you can see right here that starts with boron, then we go 2 down, silicon to germanium, arsenic to antimony, tellurium to polonium, and there you go to the very end. Okay. You'll get more comfortable as time goes on. I don't try to trick people with metalloids a lot, but definitely know to the left, the metals, to the right, non-metals. And there you go. So since we're talking about elements, and a lot of times when we think about health, there are essential vitamins, but there's also essential minerals. And those are basically elements, right? So we have major elements in the human body. So most organic compounds, the framework or the backbone of all your organic compounds, or let's say your kind of macromolecules of carbohydrates, proteins, lipids, and nucleic acids, they have a carbon backbone. They tend to have a lot of hydrogens bound to them, and then also sometimes nitrogen and oxygen, okay? So I'm looking at macro minerals, so minerals that I need a lot of it, right? That's why it's macro. You see sodium and potassium, which makes sense. The sodium potassium pump, right, in synapses. And when you study, psychology or neuroanatomy, your synapses have that sodium, the gated channels with the sodium potassium pumps. You need calcium for your bones, right? You need phosphorus and sulfur, right? Because those are part of the, DNA backbone. They're also part of the protein structure. But you also have some micro minerals you need. Oops, right? A lot of these micro minerals like zinc and iron, they end up being what are called cofactors for a lot of your enzymes. So enzymes speed up reactions in your in biological processes. They're basically a catalyst, and they have active sites. And the micro minerals like zinc and iron, they sometimes situate in the active site to stabilize the interactions to keep the shape. And a concept is you could take a look at also hemoglobin, right? So hemoglobin has iron in the middle of its heme group for the other organic bound material to it. Okay, so we're talking about the periodic table. We're using it to identify things. Now, right, the earliest models of matter were developed, believe it or not, by Greek philosophers, okay? So Democritus, this is crazy, like 400, BC, 400 years before our calendar even started, AD, they didn't have microscopes. They didn't have, advanced instrumentation, but they had their philosophy and their ideas, and they followed a scientific method as well. Although their experimentation, it was somewhat limited. It wasn't empirical. It was more based on logic and debate, right? That's how they drew their conclusions and theories and laws through debate and reasoning and logic, as opposed to empirical evidence like with chemistry, where we actually conduct an experiment and do specific measurements. But Democritus, believe it or not, he came up with the concept of atoms with atomos, meaning indivisible parts. He was the first one, okay? This is a long time ago. Unfortunately, it kind of sat around. I guess I didn't include this. I always like telling the story. About 100 years later, he was kind of ridiculed, and his whole concept of atoms was just not popular. He was kind of laughed at by a more popular philosopher at the time, and that was Aristotle, because Aristotle was a student of Plato, and Plato had believed that everything was made up of only 4 things. Does anyone want to guess what that is? So earth, air, fire, and water. And Aristotle kind of continued what his mentor believed, and he was a more popular philosopher at the time and pretty much destroyed Democritus's theory and slightly changed his teacher's, Plato's philosophy, by adding an ether as this divine other portion that's found in all material that keeps it together, which is kind of funny because now we hear things like that in comic books. But it basically sat for 2,000 years, the whole concept of atoms, until John Dalton theorized that, hey, you know what? All matter is made up of tiny particles, too small to see. Well, now we can. We have electron microscopes. We can see far smaller than just an atom, right? But he also thought atoms are able to combine with other atoms to make compounds, right? So I can take atoms of different atoms, bind them chemically, right? So they'll have definite proportions. There's still a pure substance, but now it's a compound because it's more than one type of atom with a fixed portion. And atoms are similar to each other if they're from the same element, because remember, the atom is the smallest thing you can break an element down. It's the singular repeating thing in an element. But they'll be different from atoms of different elements. So that makes sense, right? Carbon is different than oxygen or sodium. And a chemical reaction is basically just taking these atoms and moving them around. And that is totally right? We break bonds, and we'll talk about how that's electrons, so that we can shuffle these atoms around and make new bonds, because we're trying to fill their outer energy level or orbital with electrons so that they're stable, but we can take them apart from other atoms that they're sharing electrons with and then combine them with other atoms for new combinations. And that's a chemical reaction. So about 50 years after Dalton's proposal, evidence was seen that atoms were actually divisible. And what that means is there's something smaller than an atom, okay? It required, some use. And basically, it was the nuclear model. And the nuclear model basically said that the majority of the atom is empty space, okay? And it has a very dense nucleus. That's why it's referred to as a nuclear model. And that nucleus is where we find the protons and neutrons. Outside of the very dense nucleus, surrounding it are the electrons. But the majority of it's empty space. So you can almost think this like a solar system, right? A very dense nucleus, the sun, and then other planetary objects attracted to its gravitational forces, but outside of it somewhere. So these smaller divisible portions, or now referred to as subatomic particles, and again, we brought it up, protons, neutrons, and electrons, and I'm taking into account, you probably heard these terms in the past. So with subatomic particles, what we know is that if the charges are similar, they're going to repel each other. If they're unlike, they're going to attract each other. So you can think of it as, opposites attract, right? So if I have two positive charges, they're going to repel. Two negative, they're going to repel. But if I have a positive and negative, they're going to be attracted to each other. So one of the early kind of atomic models after Dalton was J.J. Thomson, who proposed what was referred to as a plum pudding model. Now, the plum pudding model is basically, it wasn't the nuclear atom, okay? I mean, it wasn't at all. In fact, with the plum pudding model, they knew that there were smaller particles than the atom, and they had charges, okay? So it was believed that these smaller negatively charged electrons, okay, were held in an atom by a positive sphere that canceled out their negative charge, because essentially we know atoms are neutral. So if there's smaller particles that are negatively charged, then there has to be positive charges to cancel it out and make it neutral. So it was believed that it was this positive sphere. So I always say, you can think of the plum pudding model more like a chocolate chip cookie, right? The cookie itself is the positive sphere, and the chocolate chips are the little electrons that are in there in equal proportion to the charge. The reason why it's plum pudding is, I mean, I guess they ate this back in the days, raisins, but they're probably little plums, but the raisins are the electrons, and then the pudding is the positive charge. Can't say I've had that myself. So Rutherford was a student of Thomson, and he wanted to test the plum pudding model to support, his mentor, his teacher's theories of that, the electrons were held in kind of empty space in this positive sphere. And the way he did it was he shot alpha particles, high-speed particles that are much smaller than an atom of gold foil at a thin sheet of gold foil, right? So the alpha particles are about 7,000 times more massive than an electron, okay? And then they have a positive charge, but they're much smaller than the gold foil. So he believed that it'll just be able to go through and not be obstructed by these smaller electrons, okay, when the alpha particles were shot through. So this was what he expected. It's actually not what happened at all. So the majority of them did go straight through when it shot through the foil, but some were deflected and some pretty much bounced right back. And that's where the conclusions of actually Rutherford's experiment trying to prove his teacher's plum pudding model is where we came up with that nuclear model that I had talked about. So the reason why it was able to shoot right back was those few times that it shot right back, it actually hit the dense nucleus, okay, right on and bounced right off. When it deflected, it kind of scraped, and that's when it deflected. Again, the majority of it did go through because the majority of the atom is empty space where the electrons are. But if it did hit that dense nucleus, it would shoot back. So that's where the conclusions were, okay, most of the atom's mass and all its positive charge are in the nucleus, and most of the atom itself is actually empty space, kind of like our solar system, with little tiny electrons dispersed to cancel out the positive charge in the nucleus. By having equal numbers of positive charges and negative charges, an atom remains neutral. So, surprisingly, the majority of it is empty space, and 99.9% of the mass is in the nucleus, held by the protons and the neutrons. So protons are not only positively charged, they have a mass. Now, the mass, relative to macro is extremely small. And I mean, you could see it because it's a negative 27 kilograms, 10 to the negative 27, but it's basically 1.67262 times 10 to the negative 27 kilograms. But that's really hard to say. So instead, they say it's roughly 1 AMU. An AMU is atomic mass unit. That's a lot easier, right? So a proton's mass is 1 AMU. A neutron's mass, again, it's 1.67493 times 10 to the negative 27 kilograms, or 1.0087 AMU, or we could say it's roughly 1, right? Whoops. Roughly 1 AMU, atomic mass unit. Now, electrons have mass, but, right, it's much less than an AMU, okay? It's about 1/2000th. And we can see that, there's a difference in the exponent of 4 right there. So it's, this is almost 10, so we could say 3, right? And 3 would be, 1,000. But it's basically, the electron's mass is roughly 1/2000th of an AMU. So it's not that electrons don't have mass, but when we look at the overall mass of an atom, electrons' mass is negligible. We're primarily looking at the number of protons and neutrons because they are much more massive than electrons. So a lot of students don't like this. So I tell students, think of it this way. You're weighing an elephant, which weighs several tons. A ton is 2,000 pounds. So elephants weigh several tons. The scale that they step on when you weigh them, its precision is to the tons, right? Because it's massive. If a flea jumps on an elephant's back, that scale won't move because the mass of the flea is negligible to the mass of the element. It's not that the flea doesn't have a mass, it's just really small. So that's the same concept with electrons. It's not that there's no mass, it's just, it's so much smaller based on the precision that we're looking at compared to an AMU. We don't even account for it because it's negligible. It's so far down in the precision that we can't get an accurate reading. So we can use shorthand symbols. Protons, P plus. Neutrons are neutral, so you have a 0. Electrons, so when you have it up like that, the plus and the minus, that's called a superscript. Okay, so that's a superscript. When it's below, that's called a subscript. Right? So submarine, under the marine or water, right? Super, supine, it's up. Okay. But when we're looking at the masses of the protons and neutrons, we're basically saying they're 1 AMU. The electron is negligible. The charges, the number for each proton's +1, each electron's -1. So if it's neutral, they have to be in equal ratios. So the diameter of an atom, right? If I take the whole atom and I took the diameter, it's 10 to the -10 meters. Now, most of the prefixes we use in the metric system are multiples of 3, right? So this is pretty close to nano, right? Which is 10 to the -9. It's between nano and pico, which is 10 to the -9 and 10 to the -12. But this is referred to as an angstrom. And when we talk about bond lengths and angles, and we usually use the angstrom to do it. But the diameter of a nucleus, that dense little nucleus, 10 to the -15, which is femto, that's 100,000 times smaller. Okay. So we've learned a little bit about the names of the elements, their symbols, how we can find them on a periodic table by using the atomic number and the groups and the periods. And now we know a little bit about the subatomic particles. We're going to use the subatomic particles in our understanding to be able to identify an element. Okay. And what makes an element what it is the proton. The proton is how you identify an element. So helium, right? Helium has 2 protons. So all helium atoms have 2 protons. That's what makes it helium. That's why on the periodic table, it was the second element listed with a 2 on the top. Aluminum has 13 protons in the nucleus. That's what makes it aluminum. So all aluminum atoms, right? So this aluminum can just has a bunch of aluminum atoms. This helium balloon just has a bunch of helium atoms in it, okay? Each atom of helium has 2 protons in the nucleus. Each atom of aluminum in the nucleus has 13. So when you're looking on the periodic table, you're going to notice not just the 2-letter symbol, but you're going to notice that number, right? Just like when we were looking at the periodic table. That number is the atomic number. That's what makes that element what it is. And that atomic number is going to be the same for all the atoms. So if I look at Na, I know that's confusing. It's natrium, right? But we call it sodium. Sodium has an atomic number of 11. That means every sodium atom has 11 protons in the nucleus. Okay, so that's how you know it's sodium. So the atomic number is equal to the number of protons. It's going to appear above the symbols. So if I look, need a periodic, that's really small, so it's going to be hard, but I'm just letting you know that having a periodic table, when you find nitrogen, okay, which is over here, you're going to look and you're going to see a number and it's got atomic number 7. So that means it has 7 protons. If you look for sulfur. I think I did this earlier. It's got an atomic number of 16. It's got 16 protons. And then barium has an atomic number of 56, so it has 56 protons. You're not expected to memorize, by the way, just so everybody knows, no one expects you to memorize a periodic table. You will be given a periodic table on every quiz or test that you're ever given. No one's going to expect you to memorize it, but you have to be able to find things and refer to it. That's why I'm constantly bringing it up to show you. Okay. So we learned that because atoms are neutral, they have no charge, then for them to be neutral, that means whatever number of protons I have is the number of electrons, right? So I could use the atomic number not only to tell me the number of protons, but it also tells me the number of electrons. So here's a little more of a detailed periodic table. And what I notice is there's my symbol. It's potassium. The name derived from the Latin name of catrium. So that's why it's K. P is phosphorus, okay? There's two numbers, okay? The two numbers, the atomic number is the smaller number of the two numbers, and it's what we use to identify the element. So the atomic number tells me the number of protons. The larger number is the atomic mass, and that's derived from the AMU. And that, where do we get the mass from? The protons and neutrons together. Okay. So the atomic number, a lot of times in books, you'll see it written as Z, it's the number of protons. The mass number is A, the number of protons and neutrons. All right. And you'll see a symbol like this. So you might see a 2-letter symbol right here. And then you'll see sometimes they'll write it as the mass number on top and the atomic number on the bottom, unlike the periodic table. So a lot of time when you're reading, they kind of flip those. Don't get confused. The smaller number is just the number of protons. The bigger number is the number of protons and neutrons. It's a lot easier that way, right? And the reason why we're only looking at protons and neutrons is because, again, there's the mass that's massive compared to electrons. We're not accounting for electrons, okay? But we can figure out how many electrons there are because there's the same number of electrons and protons because atoms are neutral. So here's an example, okay? I give you an elemental symbol with two numbers, right? I know it's silicon. Si stands for silicon. The atomic number is 14. How did I know that? It's the smaller number. So the atomic number means I have 14 protons. So the mass number is 29. What does that mean? I have 29 protons plus neutrons. So can I figure out the number of neutrons? Yeah. I take 29 because that's, right? The mass number is the number of protons plus the number of neutrons. And from that mass number, I subtract the atomic number, which is the number of protons. Right? So I take 29 minus 14, and I get 15 neutrons. Okay. So an atom of zinc has a mass number of 65. Remember, mass is the number of protons and neutrons. How many protons are in the zinc atom? Now, we don't need to do a subtraction. Like all we need to do is go to the periodic table and find the elemental symbol for zinc, which is Zn. So I take out the periodic table and I look and I'm like, oh, here's zinc. And I look, the smaller number in that box is going to tell me the atomic number. And the atomic number is the same as the number of protons. So zinc has 30. Okay. It's the 30th element, right? That's how it's organized. It's the 30th element. Why? Its atomic number is 30. Why? It has 30 protons. So how many neutrons are in this zinc atom? Well, if the mass is 65, and that's protons plus neutrons, I'm just going to go 65 minus 30. Right? And what do I get? 35. There must be 35 neutrons. Okay. So can I do that here? All right. An atom has 14 protons and 20 neutrons. What's its atomic number? Well, we already know this. We don't even need a periodic table. The number of protons is the atomic number. That's how we identify an element, 14. So what's its mass number? Well, we just said the mass is the protons plus the neutrons. I still don't need the periodic table. So I could say, all right, 14 plus 20 must be 34. So my mass number is 34 for this element. What is this element? Okay, now I need the periodic table. And it's silicon, because its atomic number is 14. Silicon's the 14th element on the periodic table as I read. So that is actually our first lecture for Chapter 4, Atoms and Elements, where I introduce elemental symbols, periodic table, how we can find the elements on the periodic table. Even if we don't have an elemental symbol, we can use the atomic number. We could also use groups and periods to help us find it. And then once we find the atom, how we can use the two numbers to determine the number of protons, the number of neutrons, and the number of electrons. So I want to thank you for watching this video. The next video that I'll be discussing is on the concept of isotopes. And what we'll notice is that when we look at the periodic table, we don't always have perfect whole, or not whole numbers, counting numbers, natural numbers. People call it integers. I don't like saying integers because integers can be 0 and negative numbers. I like to say counting numbers because we count 1, 2, 3. They're the even. But if you look on a periodic table, we don't always have these nice numbers, right? And that's because the numbers that we're looking on the periodic table are actually average masses for the atoms. And I'll be talking about how the term isotope contributes to that number on the periodic table that we're seeing after on the next lecture. So thanks for watching. Yeah, let me know if you have any questions, and I'll see you soon when we talk about isotopes. Thanks so much.